Welcome to the third video on conditional probability for year 13 of the Maths A-level for Edexcel. So chapter 2.1 and 2.2 we've established and re-established some basics even from year 12. In 2.3 today we're going to be having a look at restricted sample spaces on the Venn diagram and how we deal with those to compute the probabilities we need. Before that, of course, there are some warm-up questions, so here they are. 1, 2, 3 and 4 in total. So pause the video now and try these on your own, and when you're ready to see the solutions, press play and I'll guide you through them, and hopefully we match up and we've both got the same solutions. Anyway, I'm guessing you're ready to go on now, so let's have a look together at question number 1. So question 1 and question 2, by the way, we've got this table below showing the number of gold, silver and bronze medals won by two teams in an athletics competition. The events G, S and B are that a medal is gold, silver and bronze respectively, and we're going to let A be the event that Team A won a medal, and letter C is going to be that Team C won a medal. A medal winner is chosen at random from all these people. And first of all, we need to find the probability that that person is a gold medal winner. And what we could do with doing first of all would be to add up all of these numbers to see how many medalists we're dealing with. So if we do that first of all, you should get that there's 125 total medal winners. So how many of those won gold? Well, the ones that won gold are these here, 29 plus 21, which is 50. So 50 out of 125 people won gold, and therefore that's a probability, if we selected one of these people at random, that they would be a gold medal winner. It's this 50 out of a total of 125. And the 50 comes from the 29 plus 21, of course, and 50 out of 125 simplifies down to 2/5, or as a decimal, is 0.4. Part B looks a bit harder. Part B, it says probability of the intersection of Team A and silver medalists, but not those. So it's a probability that we select someone at random that did not win a silver medal and was in Team A. So first of all, let's just think about those in Team A who did get a silver medal. So in Team A, we've got 29 plus 17 plus 18 people. And in Team A, the ones in Team A that won a silver are 17. So the chance of selecting a silver medalist who's in Team A, the probability of selecting A intersection S, must be 17 out of these 125 people. But because we want the probability of A intersection S dashed, we actually want everything apart from these 17 out of 125 people. So if we do 1 minus 17 over 125, that's actually the probability we need. So therefore the probability of A intersection S dashed is going to be 1 minus 17 over 125, which gives us 108 over 125. And if you want to, you can do this as a decimal, 108 over 125, just so you can see this here, 108 over 125. You could have put 0.864 as well. That would have been fine too. Part C, explain, showing working, whether or not events S and A are statistically independent. You must give reasons for your answer. Well, there's a formula for proving statistical independence, which we need to know, and it's this. If S and A are statistically independent, then the probability of S multiplied by the probability of A will equal the probability of a random element being in the intersection when it's selected, where the intersection of S and A is this here. So first of all, let's just think about this in parts. So, first of all, the probability of S intersecting A, we had from before in part B's working, that was a 17 silver medal winners in Team A out of a grand total of 125 medal winners. So we need to now see if PS times PA gives us this. And if it does, then A and S are independent, and if it does not, then they're not statistically independent. So first of all, the probability of a silver medal winner is 40 over 125. That's because the total silver medal winners are 17 plus 23, which is 40, out of 125 people. In the same way, the probability that someone selected from Team A will be the total people in Team A as a fraction out of 125. So if we work this out now, it's just a case of doing 29 plus 17 plus 18. 29 plus 17 plus 18 gives us a total of 64. So the probability of selecting someone in Team A is therefore 64 out of 125. Therefore, probability of S multiplied by the probability of A is these two fractions multiplied together. And if we do that, 40 over 125 times 64 over 125, that gives us 512 over 3125. So if we just try this now, just to show that it is actually that, we get 40 over 125 multiplied by 64 over 125. And it gives us, like I've said, this value here, which as a decimal is 0.164-ish. And this one here, which it needed to be the same as, it's not, because 17 over 125 gives us 0.136. So they're quite similar, but definitely not the same. 0.136 is not the same as 0.1639-ish, 1.638 rather. So therefore they're not statistically independent, because PS times PA is not the same as PS intersecting A. So then we just conclude by saying A and S therefore are not statistically independent. Question 2, same table from question 1. It now says to explain whether or not events B and C are mutually exclusive, given clear reasoning. Well, event C is just the event that someone happens to be in Team C. Event B is the event that someone wins a bronze medal. So if they were mutually exclusive and someone was in Team C, that would mean it'd be impossible for those people to win a bronze medal. But actually, if we see here people in Team C, then actually we had 17 bronze medal winners in Team C. So clearly they're not mutually exclusive. So you could say this one of two main ways. What I'd suggest we say is something along these lines, just that it's not mutually exclusive because there's no reason why being in Team C would exclude someone from being able to win a bronze medal, unless something terribly nefarious was going off, like it was a country hosting these athletics that have some sort of horrible human rights records. That's the only way being in a certain team could stop you from winning a medal. In this day and age, no matter what team you're in, you're obviously going to be given the right to win whatever medal you are capable of doing so. So it's almost a trick question, it's that almost obvious, but just keep your head and give a common sense answer and you'd be fine. 2b is working out percentages of different amounts. So we're told here 30% of gold medal winners are female, 50% of silver medal winners are female, and 40% of the bronze medal winners are female. Then we need to find out the overall probability that a randomly selected medal winner is female. So let's just do this step by step, first thinking of the gold medalists. So for gold medalists, we've got 50 winners altogether. Silver medalists is 40, and bronze 18 plus 17 is 35. So just for the gold medal winners, we need to calculate 30% of a total of 50. So 30% of 50 is 15. So there's 15 female gold medalists. For the silver medals, this totals 40, and we want 50% of 40, half of 40, which of course is 20. So therefore there's 20 female silver medalists. Finally for the bronze, same idea, 40% of 35, and 40% of 35 gives us 14. So in grand total, the total female medal winners is 39. Then of course, if we remember that there were 125 people in total, this gives us our final answer. That overall, if somebody is selected at random, then the chance of that medal winner is female is for 39 female medal winners out of a total of 125, and 39 over 125, if you wanted to, could be given as a decimal. If so, the answer would be 0.392. So either 39 out of 125 or 0.392. For question 3, we've got a company claiming that a quarter of the bolts sent to them are faulty. To test this claim, the number of faulty bolts in a random sample of 50 is recorded. For question 3, we need to give two possible reasons why a binomial distribution might be a suitable model for the number of daily faulty bolts in this sample. I'm going to give you 4 possibilities. My suggestion is the first 2 of these 4 are by far the most relevant. I'm going to give you the last 2 of 4 just to remind you of the total number of things you could say for a distribution being suitably modelled by a binomial distribution. The first thing to say for this one will be there are a known number of bolts. There's 50 bolts, so definitely say there's a set number of bolts, therefore a set number of trials. The second obvious thing, in my opinion, to say is there's only 2 outcomes essentially. Either a tested bolt is faulty or it's not faulty. And that's a key thing we need to model something with a binomial distribution. There has to be only 2 outcomes, and this scenario here fits that bill perfectly. The other thing he could have said, probably not in this case, but in another question, could be that the probability of a faulty bolt can assume to be fixed, probability of a binomial distribution has to be fixed for us to use it. Or the fourth one, we can assume the probability of a bolt being faulty is independent of other bolts being faulty or not. And that again is something you need to hold true for a binomial distribution to be used. But these first two are the two I'd go for question 3. Question 4. Using a 5% significance level with a model of a binomial distribution, find the critical region for a two-tailed test of the hypothesis that the probability of bolts being faulty has somehow changed. The probability of rejection in each tail should be less than 0.025. What I'd suggest doing is sketching out a binomial distribution. So it's skewed to the right-hand side. I'll explain why in a moment. What I'd suggest we do as well is we label on the variable, which I'm going to call big X, and it goes from 0, where no bolts are faulty, up to 50, where every single one is faulty. I don't know if that's going to happen, but I'm going to label this on, and this here is the expected mean. It says here that we're expecting a quarter of bolts to be faulty, so a quarter of 50 would be 12.5. This is what you'd expect to be the modal value for any one of these samples of 50. So labeling the mean isn't required to give you an answer. It's not even worth a method mark. It does, however, give us a clear indication of where our values lie, and it gives some quite handy context as well. So let's get to it. So we want the chance of rejection in each tail to be less than 0.025. So we want this bit here. Oops, that's a bit too thick. I'll get this one here. So we want this bit to be no more than 0.025. The question is, what value here would give that? So we want this to be less than 0.025. And the way we do this is we just try different amounts. It's a case of trial and error, essentially, using the calculator. I'll show you how to do it. So what we do here is get into the right mode first. So we're going to press Menu, and I'm going to scroll to 7, Distribution, press Equals. Now we want binomial distribution, but we're going to go for binomial CD this time. It's because we're going to be using cumulative probabilities. Press 2 for variable, and now we want to try different actual numbers of faulty bolts so that we get a value close to, but definitely less than, 0.025. So the number of bolts being sampled is 50. The probability of one of them being faulty is 0.25. So let's go for, I don't know, let's say maybe 6 bolts out of 50 is faulty. Will that give us somewhere close to 0.025? Well, fairly close actually, 0.019. But let's see if we can go slightly higher. How about 7? 7 gives us 0.045, which is actually above for 0.025, so that's too high. So for 6, 0.019, that was the biggest value we can have, which doesn't go above 0.025. So therefore, the critical region is we could have X being up to and including 6, or as well, so the union, we could have X being bigger than some value over here. So what we want over here, in the same way as what we had for the lower tail, we want this higher tail to be less than 0.025 in area as well. So let's see if we can work this one out in the similar way. So that needs to be less than 0.025. We want the biggest value of X that will give this as being less than 0.025. We want it just to be less than 0.025. It's the first value that happens to give this is a value we're going to go for. So let's just, again, on the calculator, try something a bit higher. Let's try 12. About 50-50 chance, nowhere near 0.025. So let's try maybe 14. So the chance of having 14 or fewer bolts as being faulty is about 75%. That means at this higher end, we've got about 25%. So what we need here, to make it clearer, is one subtracted from this, subtract this value needs to be just less than 0.025. It's the first time we do that, so that 1 minus this gives us something just a bit less than 0.025. So clearly 14 wasn't there. Let's try 15. 1 minus this would be about 0.16-ish, still not less than 0.025 though, because 0.16 is bigger. Let's try 16. 0.90-ish. So 1 minus about 0.90 is 0.10, but 0.10 is still bigger than 0.025. Try 17. Now we're getting close. That's about 95%. 1 minus 95% is about 5%, but 5% is 0.05, which is still higher than this one. Let's try from 17 going up to 18. Now we're getting close. So that's about 97%. 1 take away 97% is about 3%. That's still higher than this one. If we go again, where x is 19 or less, we get this here. Now if we did 1 minus 0.986, we get 0.014, which is less than that. So the first value that generates a suitable probability of higher tail is x being less than or equal to 19. So we can write this down as well. So the chance of x being less than or equal to 19, it does say on the calculator that that's 0.9861, let's call it. 0.9861. So therefore, the probability of x being 20 or greater is 1 subtract the probability that x is 19 or less. So that's therefore 1 minus 0.9861. So if we just try this now, so menu 1 minus that probability that's stored for us gives 0.01392. 0.01392. What was that, sorry? 0.01392. Which is less than 0.025. And so we're wanting, therefore, x to be bigger than 20 for the higher tail. So for the lower tail, this would be our critical region. For the higher tail, 20 or more would cause us to reject. So overall, considering both higher and lower tails, this is our full answer. So the complete critical region is x being 6 or less, unified with x being 20 or more. So, conditional probabilities in Venn diagrams. Well, conditional probabilities can be found from Venn diagrams by just considering the section of the diagram that corresponds to the restricted sample space. So let's have a look at how that works straight away with just a worked example. So we've got A and B, which are two events, such that the probability of A is 0.55, the probability of B is 0.4, and the probability of an element being in the intersection of A and B is 0.15. First of all, we need to draw a Venn diagram showing the probabilities for events A and B. So we need something like this. So there is an intersection, so we need a circle A and B to overlap. So in terms of labelling in these probabilities, the best place to start is from the intersections. So we're told that the probability of something being in the intersection is 0.15. So the intersection is this region here in the middle, so we need to add in 0.15 in this overlapping section, like so. Next, we know that the probability of A is 0.55. So contained in the entirety of circle A needs to be values that sum to 0.55. Now I've got this 0.15 already, which is still part of the entire circle A, so the bit belonging to just circle A and not the overlap will be 0.55 subtract 0.115, which is 0.40, or just 0.4. In a similar way, for B, the probability of B is 0.4. So in all of circle B need to be numbers that add up to 0.4 or 0.40, you could think of it as. I've got 0.15 in the middle, So this must be the extra 0.4 minus 0.15, which is 0.25. Common mistake now is to think we're done, but actually we need to check in case there needs to be a number on the outside, but on the inside of the rectangle. So is there going to be a number here? Remember, the sum of all the probabilities in any Venn diagram always needs to add up to exactly 1. 0.4 plus 0.15 plus 0.25, that doesn't get us to 1. So whatever is left needs to go here. So just thinking for a second, what goes here must be 1 minus these other probabilities that are already included in our diagram. So if we compute this now and just do 1 subtract all of these values, 1 subtract 0.4, subtract 0.15, then subtract 0.25, we get a total of 1/5, which is 0.2. So therefore, we have to have 0.2 in here. So that's the Venn diagram completed. We can now use our completed diagram to tackle part B. So for part B, we need to find the probability of A given B. That vertical line in between means given the fact that we're told it's in region B. So what's the chance of selecting an item in A given that we're looking inside region B? So because we're looking inside region B, everything else apart from circle B can be ignored. We're just focusing in on the region of a Venn diagram that is just circle B and nothing more. So I'm going to get everything else to just disappear now and just focusing on circle B. So what bit of circle B would have also belonged to circle A? We know though that it's going to be out of 0.4. The fraction that would have been in circle A is a fraction out of 0.15 plus 0.25. It's a fraction out of 0.4. If you cast your memory back just a moment or two before I got this bit to disappear, this yellow bit here was actually the bit which also belonged to circle A. So the bit that used to belong in circle A, which is still part of this entire circle B, is this 0.15 part. So therefore, the probability of selecting something in A, given that the thing we're looking at is just B, is 0.15 over 0.4. So as a fraction, we can type in 0.15 over 0.4 and press equals, so the calculator converts it into a better form for us, and we get 3/8. So therefore, for part 1, it's just 3/8. So let's bring all the bits of the Venn diagram back now, so we can now tackle question 2. So that's the diagram back as it used to be. For part 2, we want to have the probability of selecting B, given that we're looking at A unified with B. So we're given now that we're looking in the intersection of circles A and B. So we can now ignore everything apart from just these two circles and the intersection. So A unified with B is everything apart from the outside of these circles. So the outside of 0.2 can disappear, and we just focus in on this intersection, which are labelled in with these very sort of jittery lines. I'm not very good at freehand writing, as you can see. So, in these binocular looking things, what's the probability of selecting something which would be within circle B? Well, within circle B, we've got 0.15 plus 0.25. 0.15 plus 0.25 gives us 0.40, which is 0.4. So we've got 0.4 out of a total of 0.8. The total of all the values in the union of A and B, add all these numbers together, the black, the blue and the red comes to 0.8. So we're just wanting a total of 0.4, which is in B, out of a total of 0.8 in the union of A and B. 0.40 as a fraction of 0.8, that would give a half. Resetting the Venn diagram again, now for question part 3, what's the probability of A dashed given that we're looking in the region which is B dashed? So if we're looking at B dashed, that means we're considering everything apart from circle B. So everything to do with circle B, we're just going to ignore and focus on the rest of this sample space. So anything to do with B, I'm just going to take away now. So therefore, the things in B dashed is just circle A, which would be 0.4, not including the intersection, because that intersection would have included B, which we're not allowed to, and also 0.2, which was in neither A nor B. So it's out of a total of 0.6. 0.4 plus 0.2 is 0.6. And if we're told that we're looking at just B dashed, which is this part here, what way could we select something that is not in A? Something that's in A dashed. Well, something that's in A is 0.4. Something therefore in A dashed would have to be this 0.2. So we're talking of as 0.2 as a fraction of 0.6. So we're just looking at this bit here, which is 0.2 over 0.6, and that would give us a third. Let's now have a look at an exam paper question. This was from a past paper, just putting together what we've seen from worked example 1 and the previous bits of the notes. So we've got 4 different events here, A, B, C and D. And for part A, we have to write down any pair of mutually exclusive events from A, B, C and D. Mutually exclusive means that the circles or regions corresponding with those events must not overlap in any way. So we can see here A and C would be candidates because A and C don't overlap. B and D would also work because B and D don't overlap. And also D and C are entirely separate, so D and C would also be mutually exclusive. So there's 3 different possibilities to select from for part A. We could say A and C, or B and D, or the final option, events C and D are mutually exclusive. Now for part B, we're given that the probability of B is 0.4. So let's just think about this for a second. The probability of event B is 0.4. That means all of the values within this ellipse representing B must add up to 0.4. All of these here, 0.24 plus 0.07 plus P, must add up therefore to 0.4. So 0.24 plus 0.07, we can simplify this. That just gives us 0.31. Now, maybe I'm a bit babyish, I don't know. I often think of it in terms of money. So that to me looks like 31p plus p, and 0.4 looks to me to be a bit like 40p if I just put a 0 on the end. So 31 pence plus something gives us 40p. What would this value p have to be? It'd have to be 9 pence. It's just 0.4 minus 0.31. In other words, p must be 0.09. So what we can do now is we can actually fill in this p. We can substitute the letter p for what the value of it actually is. So the next step, if I just bring the Venn diagram back to how it looked before and replace p of 0.09, that's now more useful to us in the future questions, part C and D. So before C, it says given also that A and B are independent. So what does it mean if 2 events are independent? Well, there is a formula we need to know. The formula for statistical independence is like this. If 2 events are independent, the probability of one event multiplied by the probability of the other has to be same as the probability of being in the intersection of those events. So the intersection of A and B is 0.24. So let's just label on this diagram this colour coding. So probability of A, I'm going to put in a blue circle, P, B in a red circle, and the intersection I'm going to highlight in green, like so. So probability of A is going to be 0.24 plus 0.16 plus Q, because these 3 things are contained within A. The probability of B, sure, we could add up these 3 values, that will work, but we're missing a slight trick. We were told earlier the probability of B was 0.4, and the intersection, A intersecting with B, is 0.24, because this value is the only one in the overlapping region where the blue A and red B overlap. So putting these values in, we have this. 0.24 plus 0.16 becomes 0.4. So this first bracket we can neaten up to give us 0.4 plus Q times by 0.4 gives 0.24. We can now expand these brackets out just like we would at GCSE. So 0.4 times 0.4 is 0.16, and Q times 0.4 is 0.4Q. So after expanding these brackets, we'd get 0.16 plus 0.4Q gives us 0.24. If we then subtract 0.16 from both sides, 0.4Q must be 0.24 take away 0.16, which is 0.08. And finally, to get Q on its own, we can divide both sides by 0.4. So divide that by 0.4, and we see that therefore Q must be 0.2. Then, because we worked out C, which is the value of Q, we can actually take Q out of the diagram and replace 0.2 because Q is 0.2. So if I just do this in the next step, say Q is 0.2, we can then tackle part D. So for part D, we're told first of all that given further that the probability of B dashed given C is 0.64, find R and S. So here we're told that we're looking at region C only. So region C, everything else can disappear for all we're concerned with. So everything else can just disappear. And we want to find out now the value of R. So looking at this, what's the probability if we're looking in region C, which is just this black circle now, what's the probability of picking B dashed? What was B dashed? Well, if I just toggle back for a moment, what was in B was 0.24 plus 0.07 plus this 0.09. So this 0.09 belonged to B. So therefore the stuff belonging to B dashed would actually be this R. Use a different color. So belonging to B dashed is actually just this R. This 0.09 did belong to B. So B dashed must be R. And the total of everything belonging to C is 0.09 plus R. So as a fraction of everything that is C, B dashed is simply R over 0.09 plus R, and we're told that's 0.64. We can now multiply both sides by 0.09 plus R, and we get this. So R is 0.64 times by 0.09 plus R. So what is 0.64 times 0.09? Well, this is what we've got one of these calculators for, isn't it? 0.64 times 0.09, that gives us 0.0576. So if we expand out these brackets next, we get R equals 0.0576 plus 0.64 of an R. We can now subtract 0.64 R from both sides to leave us on this side with 0.36 R. So 0.36 R equals 0.0576. Finally, if we now divide both sides of this by 0.36, we find what R is. So if I divide by 0.36, press equals, we get that R must be 0.16. So we can replace the letter R with 0.16, which is what it actually is. So then our Venn diagram gets like this. So we're almost complete now. D part 2, we need to find the value of S, which is here. We now need to go back to basics. Remember, the sum of all the probabilities for all the outcomes of any event needs to add up to 1 for any question, probability-wise, whether it be A-level or GCSE. So all of these values here, we need to add them all together and get a value of 1. So putting that into an equation, we'd have this. So to find S, all of these values here plus S equals 1. Therefore, S will be 1 subtract all of these values here. So if we add up all these values here to start with, we've got 0.2, then we've got also 0.16, then 0.24, and then 0.07, 0.09, and the final one, 0.16. That gives us 23 over 25, or 0.92. So 0.92 plus S equals 1. Again, thinking of it in terms of money, 92 pence plus S is £1. S must be the missing 8 pence. So S is 0.08. In other words, 1 minus the answer gives 0.08, or 2/25 if you want to leave it as a fraction, which you can. Either way around, S has to be 0.08 so that this equation works. That's all from me. Now it's up to you to try some of these on your own. So, if you go to exercise 2C in your stats and mechanics book, that's a typo, those aren't the page numbers, but it's exercise 2C. Apologies, ignore that. It's questions 1, question 2, and then questions 6 through to question 12. Try those and consult me if you get stuck, please do. Thank you very much for listening, and I'll see you all very soon indeed. Take care, until next time.